Well, thanks for watching this. I'm actually making this kind of quickly, just at the request of my students, because I hadn't made a video related to the damped harmonic oscillator. So I grabbed a couple images off the net. They don't actually go together because they came from different sources, but I'll kind of give you the basics. And this is not too much different than what's in Dr. Knight's book, but maybe just hearing it helps you a little bit. So what we're doing now is imagining we have this simple harmonic oscillator that's not so simple anymore because there's something that's causing the oscillation to decay over time. We're losing some energy somewhere. So in a typical situation, it could be friction. If you've got this mass bobbing up and down in the air, you're going to have some air resistance. So this particular model, and probably the easiest and most familiar model, the one you'll see in the textbook, is what we call a damping force. So this would be, like in this case, we've got this little thing sitting in some fluid. So every time it moves down, the fluid tries to push up, and every time it moves up, the fluid pushes down. So a lot like air resistance. And we describe this, what we call a linear damping force, which means that the faster it goes, the more force it exerts. It's a linear kind of relationship. So you see here this damping force, we would call it negative. They call it CV, but in the textbook and in the other parts on this video, it's actually going to be referred to negative B times V. So V is the velocity, and C is just some damping constant that just depends on the fluid and maybe how big this little thing here is that's sitting in the fluid. So now we've got two significant forces that are affecting the motion. Gravity is not one of them because it's acting and it's constant. It does not affect the up and down oscillating motion, but the spring does, because every time you pull down on the spring, it pushes up and vice versa. And similarly, this damping force does, because every time it tries to move down, it pushes up. So notice one of them is related to the position, x, that's the spring's force, and one is related to the velocity, v, that's the damping force. So when we write a Newton's second law equation, we take the net force, that's both of them together. So here this is the net force, negative kx, and negative, notice we use a b here instead of a c. That doesn't change anything about what we're doing other than the terminology. And those together equal the ma. And just like we did for the simple harmonic oscillator, we can change this a into the second derivative with respect to time of the position. So now, if you take this a step further, which I did not choose to include here on the video, we would also turn this v into a derivative, a dx dt. So we actually have three terms here, one of which with a single derivative, and the other which has a double or a second derivative. So we have a very different kind of differential equation to solve. And the way you solve differential equations is not how you solve algebra equations. As I describe it, you more often than not, you just recognize the solution rather than try to do some sort of step in the process. Now, eventually you'll learn more about this in advanced math and science courses, but for now we just want you to recognize it. The solution to this, in other words, what I mean is the x that is going to make this equation actually work with its derivative first and second is this right here. So I'm circling it, and it's pretty extensive. We've tried to keep it simple by making the phase constant 0 here, and the amplitude, this particular form, they call it capital A. In our textbook, they call it x sub max, but that means the same thing. So it's the amplitude times, and here's the damping part of it, e to the negative bt over 2m, where m is the mass that we're moving. B is that damping constant that here on this figure is shown with a C. T is time, so the more time that goes by, the more effect this damping has. That kind of makes sense. And I think everything else we've addressed. Here's the cosine of omega t. That's pretty much like what we had before. Now technically this omega is not exactly the same as the omega we used for undamped motion, which was radical k over m. Here it's a little bit more involved in that, but I will tell you that with the systems that we will deal with, you can use the old familiar radical k over m and you will be just fine. You don't have to worry about the little difference with the damping effect. So now we just have a bigger equation to plug into to find out where this oscillator will be as time goes by. Now, what I like about this figure is it kind of shows the total effect that this damping has. We have what we refer to as this damping envelope here, and that is basically the first part of this expression, the part with the decay, e to the negative power of t, everything but the cosine. That's the dashed line here. And then if you imagine trying to squeeze a cosine curve and not go beyond that dashed line, that is what this function here is. So kind of have a cosine curve squeezed within this exponential decay curve on either side of the horizontal axis, and that's what we get for this entire expression here. Now there's one more thing I want to mention. That's something they ask you in one of our homework problems, and that is about the time constant. We use the Greek letter tau, small letter tau, and I just want you to tell you that the time constant is equivalent to b over 2m. So you'll often see it written this way. The amplitude decays as e to the negative t over 2 tau. Oh, I said that wrong. The tau is 2m over b. I forgot it's in the denominator here. So this is t divided by 2 tau. It's a little bit ambiguous the way I typed it there, but that 2 and tau are both in the denominator of the power. So sometimes you're asked for, what is the time constant, etc. And you would solve for tau there. Now, if you don't know how to solve something that's involved in the e to the negative power, you need to get familiar with the natural log function, because that's how you sort of undo e to the power. Should have done that by now in a math class, probably a pre-calculus class if you're in mine. Hopefully you can work through that. But this, I hope, is enough to kind of give you the overall basics. And gosh, you can Google damped harmonic oscillators and find way more than you'd want to know. Just a word of caution, though, because as you saw here, we're using a C in one figure and a B in the other figures. You're going to find all kinds of different terminology used here. There's even a lot on the internet about damping systems that are not linear. So you might have something a little weirder than that. If a certain kind of fluid, maybe your damping force is proportional to the square of the velocity. That really makes this a bit messier. So I would make sure you are looking at the right thing if you're going to go looking around on the web. So, all right, I'm going to end it here. Hopefully that helps you. And check in the classroom if you need more help than this.